I have a tutorial on the inverse scattering series and say some words about the inverse scattering series for multiple people. So we did all this before. The inverse scattering series says that all of these different types of seismic processing objectives can be achieved directly and without subsurface information. Directly means no search algorithm, no aligned objective. Directly solves, like you solve the quadratic equation for roots. So, before we say what the inverse scattering series is, scattering theory is perturbation theory. What it says, what it describes is the difference between a medium and another medium, and the difference between the wave in those two media. In other words, if you have a medium and you perturb it, change it in any way, the resulting difference in wave field, how does the difference in wave field relate to the difference in medium? That's all it says. That's the whole idea of scattering. It's a form of perturbation theory. So since that's what it's about, it's natural to write two differential equations. One, let's say, for some assumed initial medium whose differential operator describing waves in that original medium is L0, and the impulse response or Green's function in the original medium is G0, and it has some idealized source here, which we all know in the real world we have to deal with that it isn't that. And then the perturbed medium means in some way you change the medium that we'll usually refer to as the reference medium. And anyway, you change it. You change the velocity at one point. You change the density at one point. You move the interface. You can make the change mild, local, global, in any one or more parameters. But somehow the medium changes from what's described by this operator to this new operator. In other words, this differential operator contains the parameters that describe a wave in the perturbed medium. The perturbation operator V is defined as the difference of these two operators, L0 minus L. So, and it turns out that this equation 1 is an identity between the new wave field, the original wave field, the new wave field, and the difference in properties, V, the difference between original and new properties. If you take this relationship, this is a relationship. You notice that G, the actual wave, is on both sides, so you haven't solved for G. But if you go through a series of approximations and say, the first approximation for G is G0, and then write G0 plus G0 B G0, and then take that as the next approximation, G, and then keep repeating that iteration, you get an expression like this. This is called the Born series or the Neumann series by physicists and mathematicians. This now is a solution for G, because G is on one side and not on the other side. It's a modeling equation. It models the medium, it models the wave. It predicts the wave G in a perturbative sense, because this is scattering theory. So, normal modeling, you take actual properties, finite difference, finite element, Lattice Boltzmann, reflectivity, actual properties give you actual wave. In this perturbation description of the wave, the wave itself is defined in terms of reference and perturbation. So, but the wave cares about the medium. The predicted wave in scattering theory agrees with everything that's conventional and acceptable. Means to predict a wave in a medium, you first have to tell me what type of modeling you're talking about. Acoustic, elastic, anelastic, and isotropic. Then you have to tell me, within the model type that you just chose, what are the parameters in detail. And so this is no different. This says you have to know L to get G. You have to know the medium properties to get G. Here, though, L is enters, the medium properties enters through V, and L0. L0 enters through G0. But everything that, in other words, this is in total something that cares about L, where the reference properties enter as the wave in the reference medium, and the properties of the perturbation enter as themselves. So, but this has a very profound meaning. It says, if you take a medium, any model, and you change something in that medium, it doesn't matter what you change the density by 1/1,000,000th of a percent. At one point, change that, or move a reflector slightly. Any perturbation between that change the property of an original medium described by V, that's the change in the properties before and after. The change in the wave, G minus G0, the change in the wave that occurs from a change in the medium is always, G minus G0 is always nonlinear to V. That's very important. So the simplest realization of this is, imagine you had a whole space which was elastic, homogeneous and elastic, and that's your reference. And suddenly, and so you put a plane wave, let's say, through it, it just propagates. Some P wave just goes unaltered through this medium. Now let's say you perturb the medium so that below a certain point you change the elastic properties so that it's now a new homogeneous medium. So you have one half space, homogeneous, another different half space, homogeneous. That perturbation V causes a reflection. Before it just goes straight through, now you get a reflection. That change in the wave, G minus G0, is nonlinear to that change. And everything that changed, anything that changed, lambda mu rho, no matter how small, the change in the wave field, the reflection, in other words, the reflection coefficients are nonlinear. That's Zopper's equation. That's the simplest realization of this very general form. So, to predict primaries and multiples from modeling, you need to know everything. First, you have to tell me what model, acoustic, elastic. Second, I need to know every property of the medium. Then I will predict from modeling your multiples. So where in the world did you get the idea you're going to predict multiples without subsurface information? Okay? If modeling says if you want to predict from modeling multiples, you need a medium. Yes? So let's understand. When you predict, let me just give you the short answer before we get to the detail. The short answer is, modeling makes data, makes the wave, and then you predict what your phone would measure. You are creating the wave in your modeling process and creating your data. In the inverse problem, you're not creating the data. The data is measured. You're given the data. The data is in your phone. the issue of separating measurements that are in your phone already, primaries and multiples, is a totally different activity than predicting from modeling. There's a big confusion in seismic in general between modeling. A lot of people think of modeling run backwards as inversion. Okay? If that was the case, we would be modeling to get multiples out. We would need model type and detail. And not, okay? Not the same. Now there is applications where if you have a medium where you, or a method where you need to know the median and the method is linear, then a forward, if it's linear, in principle linear, then running modeling backwards could be the same as an inverse. Yes. If the inverse is, if the direct inverse is linear, then modeling and inverse are the reverse of each other. If the direct inverse is nonlinear, there's no relationship to modeling. Okay. You understand? So that last equation, G minus G0, we're going to call that the scattered wave for some historic reason. And you can see here that there's a series here in powers of V. So the first term, we'll call it scattered waves of 1, scattered waves of 2, meaning it's the portion of the scattered wave which is linear in V, the portion of the scattered wave which is quadratic in V, and so on. So there's a power series, if you like, a geometric series. That's one of the big contributions of the inverse scattering series. The fact that it's not Taylor. All of our modeling FWI always thinks in terms of Taylor. Taylor doesn't have an easy inverse. Geometric has a trivial inverse. Geometric is AR squared. Okay? That's structure. AR squared. You see? That's a very special and simpler than general Taylor. Okay? Taylor would be f of x0, f prime of x0 times x, and then f double prime x0 over 2x squared, where those f prime of x0, f double prime of x0 are unrelated, independent. Here, the forward series is every coefficient is known if you know the first. That Taylor doesn't say that. Yes. You understand what I'm alluding to? Data at m equals data at m0 plus data prime of m0 delta m. That's Taylor. The reason that's inverted is no one wants to do higher. If you understood that higher is geometric, you understand? It's no big deal. Okay. So that there's a value for whatever the method is in understanding the structure here as geometric. It's much simpler than what we're assuming in seismic. The structure is simpler. The perturbative nature is simpler than Taylor. So now, so this is a modeling machine, equation 2. The inverse machine is from data, meaning from the measurements of G minus G0. In other words, in your phone, you measure everything. Let's say you get rid of the reference wave. That's what you just did. So now G minus G0 relates to V. From measurements of G, which is everything your phone measured, minus the reference wave, if it's homogeneous, just this, then how can you find from measurements V? Now, so let's say a word on the board. The fact that that's geometric is the key. If we thought of the forward as Taylor, what we're doing now wouldn't happen. If you have a geometric series, S, equals AR plus AR squared plus AR cubed. Then we know if R is absolute value less than 1, this is AR over 1 minus R. And you can solve for R. You get S times 1 minus R is AR, and S equals SR plus AR, and R times S plus A is S, and then R is S over S plus A, and this is S over A over 1 plus S over A, which is a geometric again. R equals S over A minus S over A squared. So the fact that this is geometric suggests, in other words, if in a geometric series, like the forward, AR squared, then the R is a power series in the G minus G0, going the other way. That's the rationale for equation 3. It says, if G minus G0 is a power series in VG0, if you like, yes, then V, with that heuristic, yes, can be argued to be a geometric series in the data, something which is linear in the data, quadratic in the data, cubic in the data. That's what that says, equation 3. That V, the quantity that will determine the Earth, was L0 you choose. If you can find V, you add it or subtract it to L0, you get L, the properties of the Earth. So the unknown in the inverse is V. Equation 3 is like this R business, where this is R sub 1, R sub 2. This is the portion of R linear in S, the portion of R quadratic in S. Power series one way, power series the other way. That's the argument. So the question is, okay, so now you've got a power series. How are you going to find V1, V2? How are you going to find the portion of the unknown properties of the Earth that's linear in your data, quadratic in your data? So what you do is you substitute equation 3 into equation 2. And this is due to Paolo Carvalho, sitting here, yes, from his thesis, this particular way of getting at the inverse series. And when you do that, and you set terms equal order in the data equal, you get this set of equations. I'm not going to belabor you with all the detail of that argument. But the equations here are not controversial. And they were known in different forms before us. There's a history in quantum for this, where it did no good for them, but they published it. There never was a nuclear potential that they ever found with this, for many reasons. But the machinery was there and valuable for us. The point is, here's the message, the basic message of this set of equations right here, which comes simply from substituting 3, the top equation, into 2, and setting terms of equal order in the data equal. You get this set of equations, which can solve for V1. You get V1 from your data and invert this operator G0. If G0 is propagation of water, then a pre-stack FK slope migration will get you V1. Analytic. There's an analytic inverse. It's not numerical. There's no generalized inverse. You have a formula, V1 equals. Okay? Then you take V1. What did you need to get V1? Your data and water. You take V1, put it in here. And then V1 cares about water and data, water, and so on. This whole quantity is explicitly computed in terms of water and your data. And to get V2, the second term here, you do the exact same operation that you did here. The inverse step never changes. In other words, the inverse step is analytic at every step. The complexity is in the multiplies. But multiplying data and multiplying noisy band-limited data is a lot less treacherous than making an operator and inverting it based on that band-limited noisy. In other words, what I'm alluding to is when you do iterative linear, the first thing you do is you find V1. V1 is noisy band-limited because your data is. Then you take V1 and you add that numerical thing to L0 and you make a new operator. And you right away generalize inverse, right? Where you learn more about error surfaces than you do about the physics. Okay? Which kind of optimization, and on and on. So this machinery, because it's so transparent in terms of the inverse step, allows the physics to achieve its purpose. We don't intervene in a way that it becomes a numerical issue, a mathematical issue, rather than an issue which listens to the physics as well as it can be communicated. So the point is, you find V1 directly from the data and water. You find V2 directly from water and data and water. Every term in the inverse series is directly determined in terms of data and water. So that's the story. That's the claim of the inverse scattering series. Now, if you imagine that there are certain activities within a machine that takes in your data and outputs the Earth, free surface multiple removal, internal multiple removal, depth imaging, nonlinear AVO, Q compensation. Anything that you imagine is needed from taking in data and getting V, then that activity is located within this machine, within terms, pieces of terms in this machinery. We call those isolated task subseries. Every single term, every single piece of term in this series, inverse scattering series, cares about data and water. So any ingathering you carry out doesn't change that property. And so that's its value. Now, the fact that you know it's there and your ability to find it are not one and the same. Okay? You can prove that the number of irrational numbers exceeds rational by it's a different type of infinity. But to prove a number is irrational is not simple. Okay? In fact, directly to show it is often not even possible. So, but the promise is there, and its secrets and its capability are there before we locate it. That's what's amazing. Okay? In other words, we're not making these tools, we're locating them. You understand? We don't say, well, how are we going to get this? Now, people will say, oh, you know that ISS attenuator, you didn't need to use the series. You just lower, higher, lower, you do all these things. Yeah, like, where were you before we found it? And where are you going to be when we need to eliminate it from the series? Tell us before we find the multi-dimensional eliminator, not attenuator, what it is today. And then I'll believe that we don't need ISS. You follow? It's easy after the fact to say, we don't need to derive it from that. All we need to do is copy it out of your paper. It's a lot easier. And it happens at times. But that's not a problem. I just thought to make that point. I'd like to know the thing we're working on now. Tell us how you're going to find it without that machinery. Okay? then I'll say we don't need it. Because getting it out of here is not simple. And if there's a faster way, we're very interested. Okay. Now, so there's a very important concept that you'll hear about here. There's a thing that we call innate or intrinsic nonlinearity. And there's another nonlinearity which we call circumstantial nonlinearity. Innate nonlinearity is like that Zollbridge. The only way you can get away from that kind of nonlinearity between reflection data and the change in properties is if you tell me everything. Tell me what is the world above and below, then I don't have that problem. As long as there is something you know and something you don't know, you have intrinsic nonlinearity. The relationship between data and finding that change in properties. Clear? The only way to avoid it is to know everything. If there's anything you don't know in the world, you're going to have that. There's another kind of nonlinearity that is circumstantial. For example, if you want the depth of a reflector, and if you know the velocity structure enough to locate it, that the location of that is linear. Green's theorem will do that. It's linear. And you don't need to know the velocity all over the universe. That's a misstatement of migration. People used to dismiss Claerbout. I remember working in a company where people would say, oh yeah, what Claerbout SEP is talking about, it works when you know the answer. If he knows the velocity everywhere, he'll give you the structure everywhere. Wonderful, they say. We know the velocity everywhere, we don't need that structure. Just draw the velocity. That's not understanding. You don't need the velocity everywhere to locate. You need the velocity in Claerbout's thinking enough to locate. You don't need to know below. The point being, that's circumstantial nonlinearity. The inverse scattering series says we will locate that structure without needing to know the velocity. It's going to be nonlinear in your data versus linear in your data if you do know the velocity. Okay? That's circumstantial, meaning there are circumstances where you can give me adequate information and that nonlinearity turns to linear. So here's the amazing thing about the inverse scattering series that Barstow stepped out with at the beginning. We had no idea that it was this clever. Any issue, first of all, the inverse scattering series deals with both things. Both in isolation, like in the work that Dr. Haiyan Zhang did for nonlinear direct AVO, and Hong Liang, Dr. Hong Liang continued, was the first type of activity. And the second, so for example, if you happen to have the right velocity, but you're not sure, you work hard, you get the reference velocity, you put it into the first term in the imaging series, and it gives you the conventional image. The second term, the term after the conventional, determines whether your velocity is adequate and where. And it says whether you need its help or not. That's called purposeful perturbation. The terms in the series determine from your data whether what it can produce, what it can contribute is needed in that particular data. That's amazing. And we can show you formulas analytically how it does that. Okay? We didn't design it. That's how it does that. That all circumstantial is that. For example, let's say you just have a water bottom primary. That's it. That's all you have. You put that into the internal multiple algorithm, and at the second interval, you'll get a 0. There's no internal multiple. You need 2 reflectors. So anything which involves, which is not innate, the inverse scattering series will decide whether that issue resides in your data before it finishes computing at the outset. You understand? That's a very surprising property, because our fear, and I remember with Bob in the early days of ISS imaging, we were concerned, let's say you happen to get the right velocity and this was the depth, but it's perturbation theory, so it's going to get deeper, shallower, deeper, because that's what perturbation does. It doesn't do that. If it's right, it figures it out. It's not common image gather flatness. Okay? It's a data, the image talks to other images and makes that decision. It's meaning images of different reflectors, not different angles at the same reflector. That's the difference. So it's a different kind of communication that makes that decision. So, in other words, the fear was it would be jumping around, and then if you're lucky, converge and tell you after a million iterations that your velocity was right to begin with. That's a nightmare. Perturbation theory could have been that. It isn't that. It immediately tells you, are you all right, or do you need some assist? And then, if it does, it lights up a whole set of activity. And if it says you are fine, there, the whole set of activity shuts down without you needing to get involved. So we'll give you some understanding of that. There you go. It computes an integram, which is 0. If it decides that its purpose is not called for. Okay, free surface multiple movement. This is a cartoon, very simple, but I think instructive derivation that corresponds to what Paulo Carvalho did in multi-dimension. In other words, yes, in multi-dimension, coming from the inverse scattering series. But let me race through this. Time is, maybe I won't. I'll just give you a formula. RF is the deghosted data at this receiver due to this source. R of omega is without a free surface. Down goes a spike, up comes a train of primary and internal multiples. This is down goes a spike, up comes a primary, free surface, and internal multiple. Deghosted, down, up. So deghosting is necessary here. First you derive a formula that gives you RF in terms of R, and then you turn it around and get R in terms of RF, and that's the free surface algorithm. So let me just give you that formula. It's written in many places. So the data without a free surface starts with the data, deghosted data with a free surface, and you have this series. What this added to this does two things. Every multiple that's hit the free surface once is eliminated. And every higher order free surface multiple is altered. Altered so that when this plus this happens, second order and first order are eliminated. So there's a cooperation. It's not you take second order and throw it in here. These terms, this term, this does something well and something which looks weird. It alters higher order. But in its entirety, that alteration is needed to allow that to eliminate. Yes? Again, this is not something we told it to do. This is something that it does. So here's an amazing thing right off. It works one frequency at a time. Free surface algorithm works one frequency at a time. You have 7 hertz, or 15 hertz, or 23 hertz. You take out the free surface multiple at that frequency. You don't care if you have a higher frequency, lower frequency. Think about what a shocking difference that is from modeling. With one frequency of data, you can locate the water bottom. You understand how radically different that is than modeling? Because you can't image. You need to integrate over omega to get t equals 0, yes? So something very different is going on than modeling run backwards, yes? So this is, so what this is taking a bunch, several free surface multiples, just to show you how it works. Is a primary, another primary, a free surface multiple, another free surface multiple, and this one is that one, and R1 squared, R2 squared, R1, R2. Take it into the Fourier domain, that's what it says to do, and then multiply it by itself. In the frequency domain, it says take that and square it and add it to itself. This is your data. These are several first-order free surface multiples. When you square this, among the things that happen is when this quantity squares, you get this squared plus 2 this times that. Exactly killing those free surface multiples. In other words, when you square this, among the many things that happen, is this quantity gets squared. That quantity squared is sitting here, when added to this, cancels that. So that's basically what's happening. You see here in this formula, you don't need to know what the water bottom is. You don't need to know where it is. You don't need to know whether the Earth is acoustic, elastic, anelastic. The free surface and the internal multiple codes are model type independent. They do not care not only what the properties are, they don't care what model type you have in mind. This method does not at all care about any of that. Okay? Think about how far different that is from modeling. It's modeling run backwards. Modeling starts with what's the model. This does not care. If you want, we can go through the derivation of that formula and show you it did not care. Yes? Okay, so here's an interesting example for our purposes today. This is an example that's concocted to make a perfectly cancelable free surface multiple in the primary. This is a primary, this is a free surface multiple, again, cartoon-like. This is another primary. This has been arranged for these two to cancel. Normal incidence, yes? Meaning, it's easy, make this time that time, and you make this amplitude be the negative, that's all. And so, that's what's done. So on your data, all you're going to see is this. Because these two cancel. You're going to see one event. So you take this data, but that's all you see. If you don't see it, it doesn't get processed. You follow? The algorithm says, give me your data. Well, if these two cancel, that's your data, right? And put it in the frequency domain, and square it, and add it to itself. And guess what? The second primary pops out. You understand? The invisible primary comes out, okay? In other words, this is just arranging so that cancellation, this time that, yes? And that the amplitude of the second primary to be the multiple. So you do this, you take your data, which is just, the data has one event in it, square it, add it to itself, and you got the second primary. How did it do this? It's not magic. You've told it there's a free surface because you gave it a free surface algorithm. It says if you have this event, you've got to have multiples. Yes? So it starts to act. So it predicts the negative of that multiple that it expects, which is that primary. You get it? So, why are we showing this? Why we're showing this is not any territory for adaptive subtraction. You had a primary and you had nothing. Yes? Nothing, and then a primary comes in. your energy just went up in that, yes? We made that statement, adaptive subtraction is not the tool when you have proximal interfering events. Understood. The other point here is that it's an eliminator. The Cavaglio method is an eliminator given its prerequisites, the wavelet, deghosted data, and so on. Okay, so this is Cavaglio's multi-dimensional grown-up version of what we just said. This is all this obliquity factor, which is ignored at times, ignored at ARCO at times where I work. Because you ignore it, it makes things faster. And faster matters, but not always. Depends on how, if you want to, you have a proximal free surface multiple in a primary, you don't want to save cost on leaving out the obliquity factor. And chance, well, let me put it a different way. People would like to get multiples out, but if you have a multiple near a target, they'll keep the multiple rather than chance hurting the target. So what we're talking about is a very high ambitious set of goals to cut that multiple surgically, understand? In the presence of a target. That's the plan you're about to see and some progress on. Whereas right now it's like, just leave it because the danger of cutting the target. So for us now, all things which you might have compromised, we might have compromised, are not, well, it's the history of everything. Everything that we're assuming here today, and we make assumptions later, tomorrow, we're going to make this approximation, try to argue it's reasonable. 3 years from now, that will be intolerable. Today's reasonable approximation is tomorrow's intolerable impediment. It's the nature of things. So we drop Q often and ARCO for speed. But today, that's, so this is the Arujo et al. Internal multiple code. This is an internal multiple attenuator, not an eliminator. The Cavaglio is an eliminator in principle. This is, given all its prerequisites, it's not going to eliminate an internal multiple. It's going to reduce the amplitude. So, but what does it do differently? The Cavaglio is based on the free surface. It doesn't care any history other than did it hit the free surface. How many times it hits the free surface defines the order of the free surface multiple. This works at attenuating internal multiples that do not have a downward reflection at the free surface. And what we mean by first order is how many times it's had a downward reflection anywhere. If it's had one downward reflection and any reflector, and it's an internal multiple, this attenuates it. And so that's a very, without any information. In Cavaglio's case, he has information. He has that the free surface is where it is, and it's essentially -1. Everything else is absent of information. Totally. Paulo Cavaglio is absent of anything below the free surface and needing any information. This is assuming the free surface multiple has already been removed. So this is a costly algorithm. And the new algorithms that you're going to see today that have the promise of elimination are not going to be cheaper. And that's why Michael Peroni is cheaper computing-wise. Okay, I'm gonna, this is recent results offshore Petrobras, offshore Brazil, salt layer. Andre Ferreira's thesis. This work was done at Petrobras. Focused in a piece of the line where there's a salt layering internal multiple problem.
Paolo Taringhi worked closely on that with Andre Ferrer before and after.
So the key is no other method that Petrobras tested was able to match that effectiveness. Similar for land applications. This is reports from Saudi Aramco, Chung Fu al, Yi Lo al, that they tested many methods for the ISS for internal multiple, and none were able to match the ISS in terms of effectiveness. So the status today is that we have a free surface eliminator and an internal multiple attenuator, and that they don't require subsurface information, they don't require phantom layers or any type of interpretive intervention. They do have these prerequisites that we mentioned before. We mentioned energy minimization, adaptive subtracting is the method used today, often to good purpose, often to essential purpose, but for the current problem of land and often in marine, it's not the tool. It's too blunt an instrument. We need a scalpel where it's a sledgehammer. So we're going to move on. What we are going to propose is a three-pronged strategy to deal with the problem today. And that's what this meeting's about, a major part of the meeting. What are we doing about this issue? The issue again is, how do you do internal multiple elimination, where primaries and different orders of internal multiples are near each other? So this is the three-pronged strategy. Get the prerequisites. Removal of the reference weight, the waiver, decodes the data. On land, in marine, you'll see progress. Land is where we're going for principal focus. So those are prerequisites. The algorithm itself, in principle, is an attenuator. In addition, the attenuator is first, it's not an eliminator. In addition, it can cause what's called spurious events, the attenuator. Both of those issues need to be addressed, and you'll see progress on both of them today. Meaning, if you have an internal multiple in in your data, and if it's treated as a sub-event, there are circumstances in which, when you have 3 or 4 or more generators and certain time relationships, that a false event can be created. Sometimes it's a false event called a spurious event, an artifact, just an error. Now, this series doesn't have that problem, but that term does. So you'll see work by Chow Ma looked at where that is resolved. If there's an issue with one term, another term anticipates it, locates it, put them together, that issue no longer is there. So all of the strengths of the attenuator. What are the strengths of the attenuator? Every first order internal multiple from every reflector at once is precisely predicted in its time and approximately predicted in its amplitude. Its shortcoming is it's an attenuator, okay? Not an eliminator. And it has spurious events at times. When you have hundreds of generators, you're going to have the spurious. Okay? You'll see examples from Kuwait and Saudi Aramco with how that's there and what happens when it's removed. Okay? So addressing the limitations of the ISS attenuator itself is part of what you'll see today. You'll see progress on the prerequisites, and then I mentioned last year a candidate for replacement for energy minimization. I'll just make a slide about that today. In other words, we're looking for properties that derive from the method itself, that the method has that property, so that it's not sometimes helps and sometimes not, but always aligns with the predictor as the thing to fix up everything we've left out, and this will not take care of everything. Today, we do not have a candidate for that derives from the inverse scattering attenuator for internal multiples to replace energy minimization. That's going to happen. It isn't that we did look, busy with other things, but that's a high priority for us this year. Okay, so what I'm going to do is take you through the agenda now, so you see how what we just described is going to play out. So this we just had, thank goodness. And this is, I know you're all thankful, particularly the religious people, that this came to an end. Dr. Jim Mahan is going to give a talk which says, first, these prerequisites from Green's theorem. He's going to show on complicated synthetic field data that they're achievable, and then show the impact they've made on marine multiple. So that's that one. Then the issue is, that's to motivate us to deal with land. To say, look at what we're able to achieve with prerequisite satisfaction in the marine setting. But then we move to Lynn. Well, Lynn tag is, in the marine, you're in water. And in the vicinity of the cable, that's where you need to know the properties. On land, in the vicinity of the cable, can be a horrible unknown. So Lynn is going to describe how a Green's theorem method might be able to back out that ESA property. That's step one. And then get the reference property. Step two is, then Jean Wu says, let's say we get some adequate from Lynn, reference properties for land. How do we make a Green's theorem form to predict the reference wave, including ground roll? Predict it, remove it, without hurting the data. Yes? You gotta get this ground roll in the data. Yes? Something just cut, or use some filter. Can Green's theorem deal with that? So, Jin Long is going to say, how do you take the Caballo and Araujo codes and incorporate a radiation pattern for free surface and internal multiple, and shows how you do that and the difference it makes. And then we'll show what a radiation pattern looks like on that, why that matters. We follow all these steps in the... Then Chung was going to show tests on the Encana data, and how you need to have adequate offset. If the offset is too small because it's vintage data, even though it's a very interesting, for us, possibility, because it was a simple coal generator pod and a clear reef target, the vintage of the data, 20, 25 years old, they didn't take long offset, and that had an impediment on effectiveness. It's a prerequisite. Land, current acquisition is fine. This is one. You can't process what you didn't collect. Okay, then Chow Ma is going to discuss one of the shortcomings of the ISS attenuator, the spurious predictions, and show how to deal with them and the results of that contribution. Yang Li is going to show you how to, in the 1D, which is always where we start, how to build an eliminator, not an attenuator of internal eliminator, with tests including synthetic based on I think it was sodium Remco, yes? Yes. Velocity law comes in. Then, this is a surprise, the result that came out. The difference that if you have a 1D Earth and you're doing internal multiple attenuation, how important it is to be dealing with a theory which accommodates a 3D source versus 2D. I won't steal the thunder of Jing Lu's, it was surprising what difference it makes. I thought it would be, well, you made a more realistic source, so it'll be go from effective to more effective. It's much more dramatic than that. Okay? So that's was a surprise and very recent result. Jing Wu, another pioneering contribution. Richard Coates did the 1996 or 94, published a paper for this ISS attenuator on elastic data, with elastic data. The reference medium is acoustic, and yet it was able to predict the time of including converter waves. Jing Wu is taking this to anelastic. How does it work with absorptive dispersion? In other words, you're in some salt region, deep water Gulf of Mexico, offshore Brazil. Absorption attenuation matters. How should you have confidence in the attenuator under those circumstances? Yes. So again, I won't steal the thunder, but I think you'll find that interesting. Okay. Then we have an invited talk by Michael Perrone, because you'll see that some of this, right now the ISS attenuator is a job and a half in 3D. Yes? While these new, more capable methods are not going to be less computational demanding. And so Michael's going to talk about work, new vision, and the consortium that IBM is organizing, that we're very interested in encouraging and supporting. Then we're going to move to ISS imaging. Something we're out of the multiples, and you're going to see, again, an amazing contribution from Professor Fan Lu of ISS direct depth imaging without the velocity on Mamuzu. Lightning fast, 30% longer than a single water speed FK stolt migration. You get an image which is mind-boggling. So that's a very encouraging piece of news, and we'll talk about our strategy for that when we. Then we'll just remind you of Professor Fan Lu's example, just to summarize, to give you some tutorial on one-way and two-way wave equation migration. Just sort of get to the point there. And then last but certainly not least, are two talks that talk about the amplitude properties of asymptotic versus wave equation migration for one-way waves. Chung Fu, al, and Chao Ma and Jing Wu will discuss the component within asymptotic migration that relates to the prediction of the wave field. So that's been a fascinating, interesting study. And that is going to be the two-day meeting.